Okay. So we have a few functions defined in our linked list. We have a get node function. We have an insert after function. We have an insert first function, which would in C++ standard library would be called push front probably. Let me verify that real quick. Yeah, push front. And then there's also probably pop front. Pop front removes an element. Okay. So we are not going to, in this video or in this series of videos on linked list, we're not going to try to emulate or imitate the forward list and write all of these methods like a swap method. Especially we're not going to write reverse. Probably is not terribly difficult to write. We're not going to write a sort method particularly for linked list either. But we're going to write a few more methods, a few more functions. We wrote a print function. This is also known as a traversal function, to traverse or to visit all of the nodes of. Traversal methods will be, it's simple and pretty simple in this case. We set current equal current arrow link, but we will talk much more about traversal methods when we get to the tree data structure. Traversal becomes more interesting then. We have a constructor, and once again, remember these are our member variables: the first node, the last node, and the node count. And maybe a more minimalist class linked list implementation would not include a reference, a singly linked list. And I don't want to change this everywhere right now, but again, this is a singly linked list. More particularly, since the node class only includes a link to the next node and not a link to the previous node, you might call this a singly linked list node, which is quite a long name. But if we want to incorporate a doubly linked list, we would probably say we would add a member variable to this class instead of making a change in the linked list class, in this struct rather. Same thing as a class, except the default access modifier. Okay, so we have some functions. Let's add a search function because it could be convenient. We don't have to, of course, but we're just getting some experience playing around with linked lists. Maybe it occurs to you to add some functions that are not in my slides. Okay, search function. So let's just copy this function header. That'll be a guide here. You could possibly return an integer, like the node, the index, so to speak, of a linked list, of a node in a linked list that contains the value that you're searching for. But I'm just choosing to take this approach: return a Boolean. So return true if it is found, return false if it is not found. We pass by const reference here. I alluded to this in a previous video. We're searching for a value. So it probably immediately seems to you that we're going to be doing something like this. We're going to look through the list and we're going to have an if statement. And we're going to say if the current info is not equal to the info we're looking for, advance to the next link along the chain. And if we get to the end of the chain without finding the value, then we return false. So let's declare a current node. So node of type T, pointer type, just for convenience. Not convenience, but let me try to use a consistent style and declare this as a pointer. So current equal first. So we start at the beginning of the list. I think I did the same thing here. Yeah, current equal first, except I did it in 2 lines. But we're probably comfortable enough with linked lists and nodes now that we can just we're okay with doing this in one line. Okay, so we start at the beginning. We could start at the end and iterate in the reverse direction, and that's maybe an interesting thing to think about on your own. Okay, so we say while current is not equal to the null pointer, and perhaps we set up a Boolean called is found, and we initialize it to false. So we say while current is not equal to the null pointer, and again, to show this diagram in a diagram, once we've stepped beyond the last node, we current will be set to the memory address of this pointer type member variable is going to be null pointer. So we could say that's the meaning of this. If current is equal to null pointer, we've reached the end of the linked list. And is found and not is found. I think that's how this works. And so whenever we find it, we want to exit the loop and return true, or again, the index, if you like. I think that indices are not so frequently used in linked lists. We generally don't want to have information about the position of the nodes. It's a bit of detail that is not, it's critical to arrays and dynamic arrays and static arrays, but not so for linked lists from what I've seen so far. Okay, so we say if current arrow info is equal to double equal to the value to find, the target value, return true, else only two possibilities here. If it's not equal, then it's not equal. So we step along the chain, current equal current arrow link. Okay, and I think I wrote this in a slightly different way in the slides, but I think it's pretty much the same. We'll test it, of course. If found equal to, so return, yeah, I just was a little bit more verbose here. At the end of the while loop, we return found. Okay, and then we hit the end of the search function. So a bit simpler than a bit of a simpler algorithm than the insert after function, in which we had to be careful about the order of these two statements here. If we switch these, this is a problem. I'll just leave it brief and not go back through that. If we switch those two statements, it's a problem. Okay, in search and linked list class, except we're not done yet. But we're done with the class definition for now. We can, let's collapse this and search for the value. We have these elements in our linked list. So if we say cout standard bool alpha to display true instead of 1 and 0 and false instead of 0, and we say nums list dot search for, takes a character value because this linked list is a linked list of characters, the template argument. So it takes a character. So if we search for Z, capital Z, we should find it. So this should print true. And let's comment out the nums list.print just so we're seeing single output. We saw this last time. So true. What about lowercase z? Should be false, and it is false. Now what about e? That's at the end of the list, so let's make sure we test the edge cases. That is true. Okay, as expected. I meant to say this last time, edge cases. This is literally an edge case, as in this, if you interpret the end of the array, linked list as being an edge. And what about this edge case? Can we find the element A? Hopefully, yes, we do. Okay, so that's the search function. Pretty straightforward. Testing, okay. I use slightly different code here. Nothing terribly interesting going on there. So let's write a delete node with info function. That might be a handy thing to do. And there is only one deletion. I point this out in my comment. And we're not specifying a position here, like an integer index. That might be something we might do for an array. We're not doing it for a linked list. We're deleting based on the value, the contents of the node. Like this node here, -23. If we delete node with info -23, then what should happen is this. We don't want to, is this. We don't want to, and let's just ignore the current there. We still want it to be a linked list. We don't want to do something like this and have two separate nodes if we perform the delete of the element of the node containing the value -23. So that's not a trivially easy function to write, but let's go on with it. It involves thinking algorithmically and being careful with linked lists, being careful that we don't make a node inaccessible and leave it off in space. If we, there's potential for that. If it's not clear what I'm talking about, it will be with some practice and time. Okay, so let's copy the function header again and think about it. Does the argument make sense? Yes, based on the previous example. Delete node with info. Do we want to return a new linked list, like an updated linked list, or we? That's a good thing to think about. Do we want to take the linked list object pass it by reference, but this is a member function, so it's a member, so it has access to the member variables, and the member variables are first and last and node count. And one thing that hopefully jumps out at you is if we're going to delete a single node with certain info, we will be decrementing the node count. So it's been a while since we've seen the node count member variable. But we will be decrementing, we should be decrementing it here. So presumably we're going to make some update to first and last and use both of these in this function definition. Now we're going to search. We might be calling the search function inside this code, or maybe we rewrite the search function. It will be, we say if search info to delete equal true. Let's just comment this out. We could take some steps. Maybe we would also call the get node, right? We get node at that position. But let's stick with the approach I use in the slides. So current and temp, and the new one, this is a new one, and we'll see why we need this temp variable if I explain it well. So current is not surprising. It's our iterator. Not to be confused with C++ iterators, but okay, so it's declared, and we have a found Boolean again. So this is rewriting a bit of the search function, but I'd like to approach this function definition in this way. Okay, and a temp. Let's just declare this for now, and we'll see why it's useful later. Hopefully it will be clear. Okay. So a loop and an if statement should be present here, or yeah, an if, and eventually a loop. Yeah, there's our while loop. This is the same while loop as was in it's a similar while loop as compared to what was in the search function. Okay, so if the info is in the first node, what does this look like? We're searching for the value 1. Target value is 1. So if we want to delete this node, if we just delete everything, including this pointer left off in space, let's delete this previous. We do want an update. We don't want to delete first. It's a member variable. And can we delete first? We don't want to leave first hovering off in space like this first and not attached to. It points at some. Maybe it points at it contains it is the null pointer. We want to update the first the first node of the linked list to be what used to be the second node. How can we do this? How can we move this over here and get rid of this? Okay, first I call this the simple case. We do need an if statement to see if it's the target value. So if first arrow info. So let's see, first is a pointer type. If first arrow info equal info to delete. Okay. Set found equal to true. Set current equal to first. Current is already equal to first. Okay, so current is not equal to first yet. Found equal true. None of these are initialized. Set current equal to first. So, okay. So what is this? What is this doing? And we're decrementing the node count at the end of the if statement. So let's move that. Current equal first. Let's put this in a diagram. And now we have something called previous, but current. We're not using doubly linked lists here. Current equal first is resulting in both of current being the first node and first being the first node. And we want to get rid of this node. So if we increment, so to speak, first, that is if we set first to be containing this node, this is what we want, of course, and now we can delete current. Okay, so hopefully this makes some sense. But what is an alternative approach that we might have used? Maybe we just stepped first forward. What happens if we don't have that current variable? If we didn't perform this operation, if we just said first equal first arrow link. Well, that would cut, this would cut it would cut this node containing the value 1 out of the loop, so to speak, out of the linked list. I should be careful with my wording here. But still, this node would point to this node, some node, it wouldn't be current because I commented that out. Some node would be pointing to the first node, which is an undesirable situation for a couple of reasons. One, unwanted access to our linked list possibly, and also it's a waste of space. We don't need this anymore. We're wanting to delete it. So that if we first set up this sort of, it is a temp variable, current is acting as a temporary variable in this case. Now, if we delete current, that node will be deleted, of course. But if we had not done this, we couldn't say delete first. Because if we were to delete first, that would result in this node getting deleted. Okay, so I think that makes sense without me trying to over explain it. So let's make sure we don't comment that. We set found equal to true and we return found. Okay, so this is the end of end delete function. That's it. Our return type was void, so so we set found equal to true. Okay. We're not doing anything with found yet, but we'll see. Else, so otherwise it's not in the first node. And this is an important possibility, or it is not in the list at all. So if I search in this linked list for the value 755, it's got 1, 2, 4, and again, I meant to update that to a 3. 1, 2, 3, 4, 5, 755 is not in that list. So how does the delete node with info function work in that case? But first, this else. Else it is not in the first node. So let's say we are looking for the value 2, and then we'll move on to 3. So found equal false. Again, so far, as I say in the comment here, and we set up this temp variable, temp equal first. Okay, so temp is gonna, as you can see, temp is a node type that trails behind current. And we'll make some sense of this with the diagram. Let me just copy the code. This advances to the next node. Found equal false so far. All right, so yeah, what have we done? 1, 2, 5. If we want to delete the value 5, which we probably do, just being a little silly, we want to have the linked list containing the nodes 1, 2, 3, 4. 5 is kind of, it's the thing that's out of place here. So first is here, last is here. Delete node containing value 5. So first arrow info is not equal to 5 because first arrow info is equal to 1. 1 is not equal to 5. So we go to the else block, which is here. We set found equal false and we initialize temp to the first and we step current forward. So let's let's do that with a new diagram. Let's do it from scratch. So, oops. We set temp equal to first. Oh, that was an unfortunate anchor. Okay. So I'm just pointing temp at first. Okay. And current is first arrow link. So current is here, pointing at this second node. Okay. So that's what we've done so far graphically. And so first and temp and then current. Current is here now. Okay. All right. So continuing code in the body of the else, that's a very important thing to point out. So while current is not equal to null and not found, that's a familiar condition. So we'll copy that and put it in this else body, as I said. We will be stepping through the remaining elements and asking a question: is the info to delete in this current arrow info? Are these two things equal? That's that question right here. If it's not equal, we advance along the chain. So temp is trailing behind. And again, the value of this temp variable is not yet apparent, but it will be. Okay, so let's say if it's not equal, we set temp equal current. So what does this look like in terms of a diagram? Temp equal current, and current equal current arrow length. Okay, then the else here means that found should be set to true. Because the only other possibility if they're not equal is if these two values are not equal, that means they are equal. Okay. Let's add an end while here. And this is the end of the else. The outer else. Not to be confused with this else. Okay, so what has this done in our example? Let's say that we're searching for the value 3 because we don't want to, well, if current arrow info, if we're on this node, current arrow info is 2. If we're searching for 2, then we would set found equal to true. Okay. And there are different ways to approach this algorithm, but let's continue. I am giving this example in the slides, 5 and 2. In my example, it's similar to like searching for the value 3. So in that case, the if is true, they're not equal. 2 is not equal to 3. So we set temp equal to current. So temp equal current. So now temp is pointing here, and we say current equal current arrow length. So we're continuing the search. And this is what we've done. Let me add text here. Searching for 3 ... Okay. And so we are still in the while loop because current is not equal to null. This is not null. We're not here. And the value 5 has not yet been found. So the value 3 has not yet been found because we just asked is 2 equal to 3. Okay. So we're still in the while loop. Now is current arrow info equal to the target value, which is 3? Yes. So that's true. So coming back to the code, we set found equal true because this is not true. Set found equal to true, and now what do? We want to delete that node. Okay, so so yeah, we have exited the while loop because found is equal to true. And both of these, this is not true and true, this is true and false, which results in us getting out of the while loop. Now we have an additional if found, so that indicates that there will be an else here. We'll deal with that in a bit. If found, we want to delete the node. So temp arrow length equal current arrow length, and this finally gets at the usefulness of the temp variable. It trails behind current. So current in our example searching for 3 is pointing at the node that we wanted to delete. If we just delete it, all of a sudden we have 2 linked lists, this one and this one. And how do we exit? We have access to last, which is a member variable, and first. So we can start at first and we can print 1 and 2 but we won't be able to get to 4 and 5. And similarly, maybe we could uh, come up with some way to reverse iterate through this linked list of the elements of the values 4 and 5. Yeah, we could do that as well. But hopefully you see what I just did is a problem. We can't just say delete current. At first blush, it may seem like that's the thing to do. Just delete this. But we have a temp variable here, and temp we want to set its link to kind of hop over this, and I guess maybe we want to update temp's link, and current's link is pointing at the next node in the list. So hopefully this code makes some sense. We will want to delete current eventually, but not before losing what it contains. So we set temp arrow link equal to current arrow link. And once we've done that, maybe we make this a little funny looking. Once we've done that, then we're safe to delete current. And I think it's that simple. There may be some subtleties here. Right, subtlety. So if last is equal to the current, we haven't triggered this case, but let's think about it. And would it make more sense to say if current equal last? Well, if let's go back to the original diagram and say now we're searching for 5, and test this case. Let's put the linked list back in its original state, 1, 2, 3, 4, 5. So suppose that we've gotten to this point. Current points to the last, and searching for 5. So temp is going to be trailing behind it. 1, 2, 3, 4, 5. And what would this code do in this case? If found temp arrow link equal current arrow link, and this if is, notice the indentation, if end if found. So this if statement is within this if statement after. Okay. And yeah, excuse me, that was premature. We need to move this delete current down below. If we're going to perform this comparison, we don't want to delete current, obviously, because that would be saying is last equal to something that doesn't exist. Okay, so this only occurs in one case, in the event that we have found the target value and it is in the last node, like searching for the value 5 in this case. Current is last. Okay, so what are we doing in this case? We set last equal to temp. So we update the value of last to be at this node. So I think that makes sense before we delete current. It makes sense. I'm just hopeful that I've explained it decently. Yeah, we don't set temp equal to last. Temp equal last, we'll move temp over here. Whoops. We'll move it over here. And so we don't want to do that. It's very decisive, very careful here. We don't we set last equal to temp. We update the value of last, and then we delete current. And decrement the node count. So yeah, fairly complicated function. And I think it's not quite the end of it. Node count minus minus in this if, else. Uh, okay. The else is if it's not in the first node. The first node was the simplest case, and hopefully you can see this does look simpler than all of this here. Okay, what is this else I'm referring to? Else, maybe we print a message and we say cout not found. The element was not found in the linked list. Yeah. Okay. So this website, just to point this out again, is much better at I'm doing this stuff with diagrams as best I can. But if you go to Visualgo, like visualizingalgorithms.net, and it's nice to read this information. I would say it's a silly thing not to read these instructions, this little tutorial that pops up here. Um, so let's see if we want to remove is remove the head, delete. Okay, so this is how this algorithm works. This code here. If we want to remove, let's see, what are we removing here? Removing the tail. 2, 77, 6, 43, 76, 89. Okay, that's a way to remove the tail. And I think in this particular website, there is no specify an index, remove 2, so 0, 1, 2. So we're going to delete 6. Okay, yeah, okay. So you get a similar, this is a really good website they don't have my delete node with info function, which is not surprising, but visualizing algorithms is way better on this website than me dragging stuff around. You can pause. I mean, it's better in a way. You can pause this, you can redo, you can pause, you can increase the speed at which the animation plays and so forth. And you can see, we can look at this code. Stacks, queues, double-ended queues, all sorts of data structures on this website. Okay. Testing. Yeah, we have yet to test, so let's test. And hopefully I didn't make any mistake in this function. It is 138 all the way to 201. It's the most complicated function we've written so far in this series of videos. Well, let's collapse it and just hope that I didn't make any errors. Let's see. We've got a Z. So if we say, we're going to say nums list dot delete node with info, lowercase z, let's trigger we should trigger the case. We should trigger that statement that is not in our list. Okay, using uninitialized memory temp, 183. Hopefully I can find that problem quickly. Let's open up the function definition, 183. If found temporal link equal. Okay, so temp equal first here. I'm just a little surprised because I feel like I would have caught that last semester or last year when I taught this course. Hmm. There are a number of ways, just to be safe, kind of safe. This will prevent that error from occurring, and hopefully it doesn't generate any other problems. Yeah, be careful of lack of initialization. So Z, lowercase z is not found. Uppercase Z should be found, so we shouldn't see that message, and we do not see that message. And if we print the updated list, we deleted Z, so we should see A, B, D, E. So let's see if that is in fact what we see. A, B, D, E. Okay. So what about whoops, what about that symbol? Is it in our linked list? Not found, and we print A, Z, B, D, E. So it's also nice to go ahead and print that list again just to make sure that our delete node with info function didn't do anything unexpected. Not anything obviously on it, unexpected at least. Okay, so let's test the edge cases. So we have A, Z, B, D, E, A. Now let's make sure we can delete a front node without anything bad happening. Okay, and we threw an exception. All right, so it may take me some time to deal with that. What about the last element real quick? Let me delete the last element, A, Z, B, D. Okay, that's good. That functioned as expected. Let's test one more case before moving back to the beginning of the linked list. A, Z, B, E. Okay, that seems to have worked well. A, so now let's set a breakpoint and hopefully this won't take too long to correct this problem. Okay, so first node contains A, and what's the link, the nums list? Node, 4 nodes, A, Z, B, E. I'm a little surprised by the node count being 4 and not 5. So first is containing the value A, and last contains E. A, B, D, E. A, Z, B, D, E. So that's surprising that we're seeing 4 there. Okay, we're not going to see any output for a while. Okay, delete node with info. Info to delete is going to be the value A. Yeah, A, so current, okay, current temp found. Okay, found is uninitialized. Current is null. That's an auto, sort of an auto initialization. Temp is null initially, but we're gonna give it a new value, that value, new memory address. First arrow info equal to info to delete, and it is. So we set found equal to true. Okay, and we update the position of current. We set it to first. It was left uninitialized. We set current equal first. So now current changes. And temp is a value that doesn't matter in this case. first equal first arrow link. So first at the moment contains the info 97, the ASCII value of lowercase a, but we want it to be pointing to B. Okay, and its link, if we follow that link, okay, excuse me, Z. The info contained in the link is Z, and you can see the link list by expanding this. And that was kind of an interesting choice. Let me try to shrink this or resize this. And let's see that again. First link, because I was curious about there being 4 elements here. What? Okay, so that's 1, 2, 3, 4, 5 nodes. A, Z, B, D, E. Everything seems in order there, at least to a first glance. So if we step first equal first arrow link, and then we delete for, I think I meant to say delete current. Okay, yeah, my mistake. Delete current. Let me confirm that here, that it's correct in the slides. We don't want to delete first, it's a member variable. Yeah, delete current. Sorry about that. Nobody was agonizing over that mistake. And let's stop and rerun and see if this is working in the way we expect it to now. I think we tested our other cases, so we don't need to go back and test those. We tested the other edge, E, and we tested some middle elements, and we tested not in the data is not in here. Okay, an exception thrown again. Okay. And that is in the if found. Well, nice experience with debugging. Probably another silly error. The code in my slides should be correct because I would have changed it. Okay, so let's step. Current equal first. Okay, delete current. Okay, so I'm deleting current, and then I'm trying to use it later, so that's a problem. So if found, temp arrow link equal current arrow link. So this is the problem. We're skipping that entire while loop in this case. Okay, maybe I didn't make it end if found. Maybe I didn't make it clear that the else if found needs to be within the else. Yeah, okay, sorry about that. I included that here, end else info not in first node. Whoops. Both this if and this else should be within the outer else. Okay, let's try this one more time. And we're paused because I didn't remove the breakpoint. So let's remove the breakpoint, but we didn't need an except, well, we wouldn't have hit the exception yet. And we print ZBDE. Okay, so there we go. We handled that edge case. My apologies about the irregularity there, but yeah, that's a problem with including slide code in slides like this, as I'm sure students have found out. Okay, so testing. Okay, lab 2, an assignment that I make called lab 2A. I think I call it lab 4A instead now. Should be accessible. And testing with user-defined objects. It's a good stopping point for this video, so let me just stop.